Hi, welcome back. So in this session, I would start with a very short introduction to OpenOCD and how it would change the embedded target debugging. Then I would walk through on writing a RISC-V assembly code, followed by assembling and linking and debugging the executable on Hifive1-RevB board. Okay, so let's get started. Before OpenOCD, this is how the embedded targets were debugged. So the in-circuit emulator, or called as ICE, is a device or equipment that would be provided by the silicon vendor. And this ICE would be connected to the embedded target through the JTAG port and would generate all the debug commands or the JTAG commands to read the registers or memory, or even to write the code inside the flash. So the boundary scan and in-system programming all will be supported through the ICE, and it provides the data to the host workstation and through the USB port. That's how it was. How it changed after OpenOCD is, so OpenOCD is a daemon or a software that runs on the host machine, which hosts this OpenOCD by itself hosts a large set of JTAG and Flash subsystem commands. But since it runs on the host machine, the electrical signal that has to be generated to the embedded target has to be compatible to the target. Here, this ICE would take care of generating the electrical signals, but since it's on the host machine, so the OpenOCD has to use a module called a debug adapter, which would take care of this electrical signal. But on Hifive1-RevB board, this debug adapter is on board, so that would reduce this block diagram to this. And so Hifive1-RevB board, you would just connect with the host machine with the USB cable and just invoke GDB and OpenOCD. Okay, and the OpenOCD would accept the GDB connections and let GDB to control it. Okay, and so next we would write a simple RISC-V assembly code and assemble it, then link it to generate the executable, load the executable into the Hifive1-RevB board, and debug it through OpenOCD. That's what I'm just gonna do next. So very first, let me create a new file. Call that as RISC-V assembly.ys and section.text global. Let me just add two numbers, just a simple assembly code just to show how to debug on OpenOCD. So ADDI temporary register 0, comma 3, T1. So this will basically add these two numbers from T0 and T1 and load it into T2 register. Okay, that's what I would do. And just to make sure that I don't run away from this, I just want to keep this execution here. So jump on link 0, this is like an infinite loop. Okay, let's say so I opened two terminals so that I can use one for OpenOCD and other one for the GDB. So let's see if this is saved. Yes, and I have installed the toolchain needed for the Hifive1-RevB board from here. So if you go to the Sci-Fi website and if you go to the software and if you go down, you can see OpenOCD toolchain. So I use Mac, so you can download the OpenOCD from here for your host machine, and the GNU toolchain for Hifive you can download from here. Okay, so I have already downloaded and installed. For example, if you, so you can see here, that's why I'm able to run the compiler or assembler, whatever you want to. So I just want to assemble this file, and so this is the machine architecture is RV32IMAC for Hifive1 or for the core FE310 core, which is inside the Hifive1 revision-V board is RV32IMAC ISA. Okay. So what another option I would want to give is no attributes. Okay. I'll come back to this later and tell you why I want this. Generate. Let's see if this is compiled. Yes. Okay. So the object file is generated. So if you want, let's see if that is funding RISC-V. So it's an ELF32 because RV32 IAC, so it's a ELF 32-bit format, and it is Little Indian RISC-V, and you can see this is exactly the code, and you can see the address is still at 00. It starts at 00 because it's not linked, just it's assembled. Okay, so next we should link it, but to link we need a linker script. Before we generate the linker script for the linker, I just want to show you what would happen if we don't remove the arc attributes here. So this object file will have a bunch of attributes, RISC-V attributes. I'm not sure how this is used. So that's it. So that's the only difference. If you need these attributes, then you keep it, but I don't know how these attributes are used, and I don't find anything useful here. Okay, but for now, so let's create the object file without the attributes. So okay, so that's so cool. Good. So now let's create a linker file or linker script for the linker. Okay. So let's output architecture is going to be RISC-V, and you need an entry point and main. That's what we have, and I'm just gonna write a very simple linker to map the code, because if you see the assembly file, there is no big it's a very simple code. There's not even a global data, so I'm just gonna write a very simple linker script which would just load that code into the RAM, okay, and execute from the RAM section. So some name, we'll call it as RAM data, and attributes we need write executable and whatever, everything. Okay, we can just give all attributes. Let's say origin. So let's see the memory map of Hifive1-RevB code. If you go to chapter 4 here, so the RAM address starts from 8 followed by 7 zeros in hex. Okay, so on chip volatile memory. So 0x 8 1 2 3 1 2 3 4. Okay, and length equal to 0x. Okay, so as you can see here, the length is up to 3ff. That's it. Sections. I have a dot section here, so I will just map the text. Stop anything from the dot text section shall be put here, and that's it. And I will just align. Let's try to link ld-t. You can give the linker file with the -t option and linker.ld, and you give the object file and you generate the ELF. What is that? Which file? LENGTH. Okay. And it should be equal to, what is that, line 14? Now that the syntax errors are gone, okay, so now we need to specify the ELF format. So this and -b. So the ELF is generated, but we have a warning: cannot find entry symbol main defaulted. Okay, we don't find main. Okay, underscore main. So the entry point should be underscore main. Okay, cool. So that's the ELF file. Let's see if we jump the, or if we do an object dump on the ELF, we can see if it sounds good. Now if you see the, after linking, the target memory destination has been changed, which is the RAM address start. So now this ELF is ready to be loaded into the target. So let's run the OpenOCD, and then we can use GDB to connect to OpenOCD and load the ELF into the target. So for OpenOCD, we need a configuration file. You can take this config file from the internet. There are many examples, but so mostly the most important things that should be on this config files are the about the debug adapter, a driver, and the transport protocol which has to be used here. In this case, it's going to be JTAG, and these are all like a couple of macros that has to be set. These are all used by the OpenOCD tab. So this is ID for the Hifive1-RevB board alone, okay? So set target. Mostly I would just copy an existing OpenOCD file and change few things to use that. That's what I'm just using here. So that's what same I'm doing here. I just took an OpenOCD config file for from Sci-Fi for some other hardware, and I just modified it and create. I'm not an expert in OpenOCD. So you create the target, then you just configure it. So you have to give the works physical memory where OpenOCD should work on. So in this case, it's going to be the RAM address 1234. Okay. And work area size should be 0x4. And we don't need a backup. Okay. 0. Then I just write it on the back. Okay. And let's turn off the physical, virtual memory. So we don't need the virtual to physical, virtual memory space. So this off and this way set underscore. And then these three are standard in it. Then should like 3 and then you halt. Okay, but so these. So this target create and this one I just copied it from the Sci-Fi's OpenOCD config. So once this config is ready, all you need to do is OpenOCD and do this configuration file, and it should be able to read my, okay, what it says. There's a lot of unknown param work. Okay, there's just a typo. That is a 12. There is this. What is next? 15. Okay, 9:15 should be RISC. Okay. Okay, now let me Control C and clear and run again. So once you generate a config file based on your ID and the transport protocol, everything, then once you run the OpenOCD, it should be listening on this port. So for GDB, it's going to be port number 3333. Okay, so on the other terminal, so what I'm going to do is GDB and there's some .elf. Okay. Yeah. So if you notice here, it says the no debugging symbols found in RISC-V. That's the reason is that when I assembled the object file I did not give the -G option to generate the debug symbol. So what I would just do is quit and go back to the assembler again and assemble RV32UMAC -TR and -G. This would create the object file with debug symbol. So just assembly.s okay, and I'll read link again linker.ld and just file up. Output should be .elf and elf32 RISC-V. Okay, so now the ELF is ready. I'll just cancel this and relaunch the OpenOCD. And GDB and ELF. Okay, now you can see. So from GDB, let's connect to the server, which is the OpenOCD. So get extend remote localhost 4. Okay, and you can see now the ELF is not yet loaded. So let's load the ELF. So it says that okay, it's loaded at the start address of this and totally just 12 bytes long because it's a very small code. And let's step in. Yeah, so it's now at this line. So info registers would give you the values. So T0 is 3 now, and it's already executed. So T1 and T2, these are the 3 registers that should be modified after stepping in 2 more times. So let's step in and come back and see what is the value of T1. And 4 registers. Yeah, so the value 5 is loaded on T1. And now you can see the sum of those two numbers, which is 8, as in T2. So you can, so that's how you can debug and run your code and test using OpenOCD, and it's very powerful when you develop a driver or low level where you don't have the even the std out or the printouts are not yet ready. When you at that level, if you want to debug or write a code, and then this is very, very useful. And as you see, how is it? Yeah, it's you, but this comes with the cost that you should know a couple of GDB commands and how this entire things work. Otherwise, you might find it difficult. But what it gives you is the create control. That the amount of control it gives when you test the lower code is great. For example, this linker, whatever I created here. If you see here, I can mention the address where this where my assembly code has to be loaded. And most importantly, if you see that the linker doesn't mention anything on the flash, because when I test my code, I do not want to write something into the flash and later turn the board into a state where it cannot be recovered. So RAM, you can test the code, and then when everything goes well, then you can extend this linker to support flash, and then you can move this code into the flash. Okay, and in that case, you have to even modify this OpenOCD to support the flash write as well. And so yeah, that's pretty much that's the end of the session. And please let me know your comments. Oh, thank you. Yeah, see you in the next session.